Hi, everyone. My name is Benny Isaacs. I'm a senior security researcher at Wiz, and today I'm going to present you the vulnerability that we have been exploited earlier this year in Pwn2Own in Redis. So a little bit about myself. I've been researching for the past 11 years, and I've been researching Windows, IoT, Android, and Chrome. But now my main focus is on the cloud environments at Wiz. But today, it's all about Redis. But why? So Redis is one of the most used in-memory DB in the world. It's being used in 75% of the cloud environments. The bug that I'm going to present today was introduced 13 years ago. By the way, this is me 13 years ago committing the bug into the Redis. Awkward. Just kidding. And the exploitation was really complex. It was 2,500 lines of code. And we had only 1.5 weeks from discovery to RCE. So here is me and my colleague literally waiting for a flight to Pwn2Own and doing last-minute adjustments. So the CVE just got discovered, patched last week, and was disclosed by Redis. It was discovered and exploited by myself and my colleague Nib Bracha, who couldn't be here today, and we successfully pwned Redis during the Pwn2Own in Berlin. So this year, Redis introduced the AI category for the first time. So when I went through the list, I saw that Redis had the biggest prize. So I said to myself, why not to try pwned Redis? It's cool, it's challenging, and here we are after a successful pwn. So in order to understand the bug, we first need to understand the attack vector. So Redis, by default, allows you to run Lua scripts. So in this example, you can see that I'm sending hello.lua script, and we get back hello world. It's important to understand that the Lua interpreter is a very minimal and sandbox environment. For example, you can't even do print hello world. And you can't even load libraries, you can't do anything. Basically, just mathematical and some atomic operations on your DB. So today we are going to focus on the function load. The load function takes a callback, and it will call the callback to get code chunks. After it gets nil, it will take the code chunks, and it will create an interpreted version of the code. So in this example, you can see the getCode function callback, which on the first call, it will return the string print hello world, and on the second call, it will return nil. So after we call load with this callback, we actually get a function that we can call, and it will do print hello world. It's really important to understand that the load function gets as a parameter chunk name, and when absent, it defaults to equal load. Basically, the chunk name is mainly for error handling and messages and debug info. So let's talk a little bit about the Lua internals. So the Lua is basically managed by, there is a GC to manage the memory. So the GC basically tracks every Lua object. So in order to do that, it has the GC header struct. You can see that the GC header struct has the GC object, which is the next object, the TT field, which is the type field. Like, for example, if it's string, it will be string. If it's int, it will be int, and etc. And the really important field is the marked field, which the GC used to determine if the object is being used or not being used. In the right example, you can see how the T string, which represents a string in Lua, looks like. It will have the GC header, it will have hash, len, and it's really important to understand that the data itself of the string will come right after the header. It won't have any pointer to data or something. It will just be adjacent to the header. So in the example above, you can see how you initialize a T-string, for example. My string equal AAA, and it will wrapped by a T-string object. So Lua has a quite basic GC. It's just basic mark and sweep algorithm. So basically, it will iterate all over the Lua stack, and it will iterate each object, and it will mark any object that has reference from other Lua object. So in that example, you can see A linked to C to D, E. So all those objects are marked and won't be free because we are using them. But in this example, the I object is not referenced by any other object. Hence, it will be free. So now that we're knowing a little bit about Lua internals, let's dive into the bug. So as I told you earlier, we are going to focus mainly on the load function. The Lua B load is the C implementation of the Lua load function. So you can see that there is a C string that is initialized with the equal load. This is because in our example, as you can see, we didn't supply any chunk name. So the default will be equal load. It's important to understand that in this moment, it's only a C string. It's not T string or something like that. Later on, in Lua Y parser, which take an argument, the name, and it wrap the name with a T string. So from now on, the equal load string is now tracked by the GC because it's a GC object from now on. So from now on, the GC will track it. You can see in the first line of the function, it's important to note that there is an internal struct called leakState is initialized on the native stack. It will be important for the next slides. Oops. So the T-string you can see in the highlighted code is saved to the leakState object, which is, as I said earlier, initialized on the native stack. So now we will have a pointer from the leakState to the T-string. After a while, the Lua X set input called the next function. The next function actually call our callback. And in our callback, we are doing a bunch of stuff, but one of the important stuff is that we trigger GC. It's really convenient, not like in Firefox, but it's really easy. You can just run collect garbage, and the major GC will happen. So in this moment, we trigger the GC. Now let's take a look how what the GC will perform now. So as a reminder, we have the leakState object, which saved onto the native stack, and it's not tracked by the GC. So from the GC perspective, the T-string doesn't have any reference from other Lua object. Hence, it won't get marked, and it will be get free. So it's getting free, but we still have a dangle PTR from the leakState. So now the leakState pointing to a free memory. So this is where the free happens. This is the critical moment where the free happens. And we now, of course, need to talk about the use, because this is a use after free vulnerability. So let's talk about the use. So in Lua, we have a proto-struct, which encapsulates everything that the VM needs to execute a function. And specifically, it includes the source field. You can see that it contains a field to a source, which pointing to a T-string. And you can see that the openfunc will actually take the source from the leakState and will assign it to the proto object. So from now on, we will have a pointer from the proto object to the same dangle PTR. We will have the same dangle PTR to the free T-string. After a while, we called the load function called fparser, and you can see that it will construct a closure. What is a closure? Closure is a function in Lua, is an object in Lua that represents an interpreted function. So basically, load will return a closure. So after that, you can call this function. So the closure is constructed, and you can see in the highlighted code, it will have a reference to the proto. And in the couple last 2 lines, you can see that we push the closure to the Lua stack. So now the situation is like that we have the Lua stack, we'll have the closure pushed onto the Lua stack, and it contains a reference to a proto, and it's containing a reference, a dangle pointer, to the free T string. So the function generic reader will call our callback, and we do a couple of other things here. So as I said earlier, in Lua, it's really convenient. You can troll the GC. So we actually call collect garbage restart, which will do is assign the GC threshold to be equal the G total bytes, meaning that the GC will need to happen very soon. We have the 2 couple of lines after the restart, the step and the set step mule. It's because we want to fine-tuning the exact moment where the GC will happen and the size of the GC cycle. So after returning from the callback, the generic reader will check the return value. You can see that if the return value is invalid, which in our case we return an invalid value, it will call the Lua L error, reader function must return a string. And in Lua, you can register your own error handler, and Redis did one. And basically, we need to understand that they call debug.getInfo. And what debug.getInfo, it really doesn't matter what it does. The important stuff is that it try to allocate some Lua object. And when you try to allocate Lua object, there is a check if we need to run GC, if we have enough space. So you can see that there is the if total bytes equal or greater the GC threshold. We know it's equal because we set it like that. So it will trigger a GC. So now let's take a look what happened when the GC now happened. So remember that we had the closure on the Lua stack. So we will start and traversing the closure. And it has reference to the proto. So now we will traverse the proto. You can see here the implementation of the traverse proto. And it will actually will mark the string, the same string that we saw earlier, the F source. And the marking implementation, you can see in the definition above, is just resetting 2 bits of the marked field. So you can see in the diagram below, we have the T-string GC header, and let's say that the marked field is FF. After the use is being triggered, after the GC is finished, it will be FC. So as we can understand by now, we have a use after free, where the use primitive is to reset 2 bits. The 2 bits are in constant offset, and we don't control the string. It's always the equal load string. So we had to think what the hell we're going to do with that. So we wanted to reclaim the free string, the free T string, right? So we tried to find an interesting candidate. The candidate that we looked for was the Lua table. The Lua table basically is, we can think about it like a Python dict. Okay, so it will have nodes, and each node we will have the T value and the T key. And the T value can be what Lua object that you want. It contains a pointer to the data itself, and the TT, which is the type of the object. So you can see that the table has a field that it's called node, which is a pointer to node. So the idea here is to try to reclaim the T string with the table, so the node pointer will fall on the exact offset of the marked field of the T string. So that's what we're going to do here. we had some troubles. We did a lot of heap shaping. We had to fill the T cache, and we had to do actually heap consolidation because the table is larger than the T string. So we did a lot of heap shaping, and we actually succeeded to achieve that the table will fall on the exact offset of the T string marked field. So in the diagram, you can see that the node pointer is on the exact offset of the marked field in the T string. So actually, once the T string mark is being happen, it will actually corrupt the node pointer. I know what you might think. What happened if the original bits are zeroed? We will do nothing, right? So we can understand it in our exploitation flow, and we just retry it because our chances were 75%, and we wanted 100% for Pwn2Own. So we just do a retry. We clean everything. We don't crash, and we can just retry again. So it will look something like that. We can see the spray table has a pointer to the original node. Let's say the original node is an deadbeef address. So after the use after free is being triggered and it resets the 2 bits of the marked field, it will shift the node pointer to the back. It will be 100, 200, or 300, depending on what address. So in the original spray, we sprayed a lot of nodes as well, so it will be false. So it will be false on all options that could be. So now we have a table that's pointing to our fake node. So we, of course, need to know how to fake nodes. So I'm going to talk about it now. So basically, we have the T-string object, right, which is just a string. So we can just fake whatever we want. So in this example, we can just allocate a T-string and to mimic the GC header, the other fields, but we have a pointer to a node. So in order to do that, we need an address leak. So we were really lucky. In Lua, there is a feature. If you call toString on an object, which is not string, you will get its address. So if you do toString on my table, you actually will get the address. But if you're doing it on tstring, you won't get the address. So what we did is something like that. We will allocate a random object that will be the same size of the string, because we want that the string will be adjacent to the my table, and then we can calculate the address of the string. So it will be my table address plus size of my table. But nobody guarantees you that the string will be right after the my table. So we are allocating one more object after the string, and we calculate the distance between my table 1 and my table 2. If it's the size that we're expecting to get, we can assume that the leak string address will be where we expect to be. So by doing that, we now have the address of any T-string that we want to get. So now let's back together to the object faking. We can fake a node, and we can fake any T value, which means that we can fake any object in Lua. So in this example, we're faking a table object, and we can get the T-string address because we have the leak primitive. So basically, we will fake a node, and that will point to a T value, and the T value will point to the leaked string. And from now on, we can fake any object that we want. We can do infinite reference to other objects. We can play it around, and we can do anything that we want. So every good exploit needs an absolute read, right? So we needed it for construct job chain. We needed to construct to get some pointers of the pointer guard to bypass the pointer guard. So let's say we want to read the address 500. We can, of course, just fake a t value of type t string and just read it, right? But actually, it won't work because we need to consider the header. So we will fake a t value that will point to the data that we want to read minus the t string header size. So by doing that, we now have a fake t string, and we can just read its data using string.sub, and we can get a substring of that data. Of course, that the t-string header could be a garbage, but actually Lua doesn't care as long as the length that you want to read is above or equal the data that you want to read. So if the length is not equal or above the length that we want to read, we can just take back the t-string header and add to the data that we want to read until we find a bigger length. So by doing that, we can actually do absolute read. So by doing that, we will construct a job chain. We calculating all the gadgets. We are finding the gadgets we parse some elves, and we construct a job chain that eventually we call system. But we need to trigger it somehow. So luckily enough, we have an Lua object called cClosure, meaning it's wrap a C function, because in Lua you can wrap some C function and call them from Lua. So basically, we can fake a cClosure that will point to our job chain. And after we are faking this object, we just need to execute it. So after we execute the cClosure, we will actually trigger our job chain. So let's wrap it up. Basically, we trigger the use after 3, which reset 2 bits. The reset 2 bits will corrupt the node pointer, and we can then bake some references to any other object that we want. We can fake any object that we want, so we can construct a cClosure. We can read elves. We can read, for example, OpenSSL to get the pointer guard and bypass it, and we construct a job chain. We will start the cClosure, and it will call the system. And we get the 40K from Pwn2Own. So now I will show you a live demo, which I hope will work. After the first attempt, I'm not sure about it, but let's try. So here we have a Redis instance on the left, and we have the server, which is just netcat listening, and we will have the exploit. So it's a little bit slow because of network constraints here. It's running on my EC2, but let's see if it works. Yeah, it's pretty slow. You can see on the right side, we had a lot of debug information because if something will screwed up in the Pwn2Own, we will have some debug info to actually fix it. So you can see that we leak the T string, and you can see the 2 objects, and we calculate the diff between them. So yeah, just a couple of seconds, and I hope it will work. We, of course, can fail due to bits that are 0 out, but the exploit will just do a retry, because if you don't crash in Pwn2Own, it's still considered 1 attempt. So yeah, it worked. Now I have remote shell, and if I do who am I, we can see it's Redis. Yeah, that's it. So unfortunately, I had to simplify some concept because the exploitation was really, really hard and complex. But in the future, we might featuring a blog containing all the technical details about it. And we didn't want to publish a POC because there are many companies that are still vulnerable, and we are waiting for them to upgrade their Redis. So feel free to ask me anything, LinkedIn, Twitter, talk to me later. I will be more than happy to answer your questions. Thank you.